You are all set. Thank you, Jim.
Now, I got to get back to the beginning. There we go. Well, thank you all for joining. I'm very pleased that I see some of the folks that I know on this already, and good friends through Facebook, or former students or former colleagues. I'm very pleased with the turnout tonight. I want to talk about climate change because it's very, very important. It has been sort of a area of interest and passion for me for a very long time. I began studying it when I was working in graduate school. By then, we were more worried about not global warming, but global cooling. And boy, have things changed. And 3 key points for the presentation tonight. Whatever you call it, it's real. And there's a lot of controversy over this, and we'll talk a little bit about it. Climate change affects everything, and it's going faster than previous changes. The Earth has always changed, the atmosphere has always changed, but over long periods of time with slow change. And now it's changing very fast, and that's not good. Organisms can't adapt, they can't evolve, that sort of thing. Because climate change is caused by us, it can and must be fixed by us. And there's a lot of controversy, I guess you'd say, in terms of whether or not people are in agreement with the kinds of changes that are produced or proposed, and those that are not. So, various kinds of new ideas are not easily accepted, and climate change is also one of those. Human response to scientific discoveries that challenge the status quo have always been faced with prolonged and fierce resistance. Examples abound, and a basic good one is Copernicus and Galileo with the idea of a heliocentric universe or solar system versus the Earth being sort of the center of all things. This resistance is particularly true if there are religious or economic systems or common sense getting in the way, when the action or change is required, particularly if that requires sacrifice. If people don't understand the science, and climate change is a very complex topic, and so it's easy not to be in the loop to understand particularly all the details. We're not going to go into many of the details tonight, but we'll provide a basic understanding. And there is a disinformation campaign going on, mainly by fossil fuel interests and other interests that feel that there is a financial stake for them if we proceed. What do we need to do? We need to lower carbon dioxide and methane emissions. This is something that can happen just by stop burning fossil fuels. We can safely remove what we've burned that is created by what we've burned and move it to geologic storage. We can plant trees. We can paint roofs so that the heating isn't as severe. We can do geoengineering. There's all kinds of things we can do, but there's no real clear path. What we really need to do is lower carbon dioxide and methane emissions. This is collectively called mitigation. We mitigate what is causing the problem. We also need to adapt, and that is to change. We need to change to prepare for bad consequences that are already built in due to past and future emissions. Some of this is already going on. In some cases, it isn't yet, and we should explore ways to do this. Well, what's going on here? Okay, both mitigation and adaptation will make things less bad, and could ultimately lead to much good and actually increased economic prosperity. We need to do both. We need to get going. To do nothing will lead to further problems and suffering. First of all, climate change is real. This isn't a new idea. It's an understanding of basic physics, and that came about in the late 1800s by Svante Arrhenius and T.C. Chamberlain, a Wisconsin guy. He was president of the university, and he was very much involved in looking at weather and climate and geology and all kinds of things related to the Earth. Both of these guys thought it would be a good idea to have global warming because they felt that the cold was an inhibiting factor. More recently, James Hansen from NASA sounded the call that we need to do something about this. By this time, you could see that carbon dioxide was increasing by a great amount. Those early guys, they saw the Industrial Revolution going on, but they didn't know quite how much carbon was putting into the atmosphere. They knew what carbon would do. It would lead to warmer temperatures, but they really didn't know the magnitude of it. Hansen was probably the first guy that did and presented his findings to the political groups, the Congress, and the general public. Now, this is basic physics. Increases in carbon dioxide cause more heat to be trapped in the lower atmosphere. And this is kind of a busy diagram, but I'm going to walk through it because it's important. Sunlight coming in is absorbed by the Earth's surface. Some of it's reflected off of clouds. Some of it is reflected off the surface, particularly if it's snow or ice covered. And then some of it is absorbed by the atmosphere. Most of what is absorbed by the surface heats the surface, and that is absorbed and re-radiated in the long waves. And this you could think of as heat energy, and it puts it back out. Now, this would go out to space again, and some of it does, but there is an inhibiting factor, and an important one, of clouds and greenhouse gases that essentially heat up from the ground below. The Earth below heats up the atmosphere and the greenhouse gases. They, in turn, radiate heat back to the Earth, and it is this loop that causes what we call the greenhouse effect. Now, we couldn't exist as life on Earth if we didn't have the greenhouse effect, so it's a good thing. But an enhanced greenhouse effect is a problem. This greenhouse gases here, to some degree clouds, provides a blanket. And so that every time the loop goes around, the blanket warms, goes back to the Earth, comes back out, warms the blanket, and it keeps going with a little bit escaping each time and some emission from the atmosphere. If this blanket gets thicker, then we have an enhanced greenhouse effect, and too much heat is stored, too much goes back to the Earth, it heats the surface, it heats the atmosphere, and we've got global warming. This has all been laid out by the Intergovernmental Panel on Climate Change, and this is a group from the UN that has studied all of this stuff over the years. They come out with periodic reports. This is the most recent one, and as time has gone on, this has become a forum, in essence, for all the world's countries to present their recommendations, present their research, their findings, and then their recommendations of what should occur. Because so many nations are involved, some nations that are big emitters, some nations that are getting hit by some of the effects more than others, it tends to be a fairly conservative report. And thus, it is, as some people would say, fairly tame in terms of what it says is going to happen. In the United States, we have the U.S. Global Change Research Program, which is a group represented by every federal agency, and they also do a national climate assessment. And this assessment is regionally based, so you can get into greater detail, and it covers the science, it covers the effects, and it tells what could happen. It also provides recommendations for what to do. One thing that's not in disagreement really is that 97% of the scientific community in the climate science realm agree that global warming is happening and that it's not good, that is caused by us. This is sometimes disputed by people that deny climate change, but a good search of the literature will show that virtually all of the climate scientists do agree. And in multiple studies, study after study, it shows that they're finding the same stuff, and that measured and observed conditions show current warming and the results of this warming. This isn't models. This is what we see in front of us today. And the Earth is instrumented very well to capture just what's going on. The models predict future warming with increased future emissions that are already sort of built in. And models have some differences in sensitivity. Some people don't trust models. I think models are getting better. And I think they're pointing us in the direction of what's happening and where we need to go, but they're not completely foolproof. But measured and observed conditions are pretty foolproof. Climate change is not good and will get worse. The last time greenhouse gas concentrations in our atmosphere were as high as they are today was 3 million years ago. That's a big problem because we have adapted essentially as human beings in the last 1 to 2 million years ago. And most of the world's plants and animals, most of them have attained what they are today over the more recent time. And so we're changing something that's very, very fundamental in terms of what drives the atmosphere and what causes the increase in temperature and other phenomenon in the atmosphere. And virtually all of this increase has occurred from the burning of fossil fuels in the last 200 years since the Industrial Revolution. We know about this because we can gather settlement cores from the ocean bottom. And these sediment cores are datable. They contain a lot of evidence for how much warming has occurred over a very long period of time, and maybe 100 million years in some cases. They also have datability with paleomagnetism and lenses of volcanic ash that appear in here that can be dated. So we know what was going on when. And we know that temperatures of what was going on then was associated with greenhouse gases of a certain sort that was fueling certain kinds of organisms with their carbon content and that sort of thing. And we could say, hey, it was a long time ago since we had greenhouse gases this high, and this is what's likely to occur if we continue on through the record. Ice cores go back about 1 million years, and that's certainly not as far back as we can with seafloor sediments. And I've worked ice as well, and they gather ice from Greenland and from Antarctica and from mountain glaciers, and this ice traps greenhouse gases. So you can actually get the original gas from a particular time. This is also datable because you can sometimes see the layers that can be counted up in years. And you can also get lenses of volcanic ash that tell you the date through radiometric methods. And I've worked with these things. You cut slabs of this, you put it into a melter that captures the gas that's evacuated and captures the gas uniquely to that lens of ice. And then you put it into a mass spectrometer, Pocari device, and it tells you what the gases were or are in that lens of ice from that particular time. So we've got a good idea of the paleoclimate. We also can use things like tree rings and other kinds of indicators that cover different time spans. Fossil pollen I've worked with, and we can get a good idea of the past, and sometimes that gives us an indication for the future. The tie between the carbon dioxide emissions and the warming and of the lower atmosphere and the ocean is well established. It's basic physics. People in the scientific community that deal with climate do agree. And if these emissions keep increasing, improving climate models can predict the temperature will continue to rise, and mostly bad outcomes will be associated with temperature increase. Not always necessarily in ways predictable in the sense that it's going to be colder here or warmer there, because the world is big and the atmosphere moves around, but things happen and they accumulate. The effects are worldwide: the atmosphere, hydrosphere, lithosphere, cryosphere, and biosphere. Essentially, the whole world system is interconnected and all are affected, and so will we. And we are feeling the effects globally, also here in the US particularly, and we'll go into some of the examples, and less dramatically here in Wisconsin right now. So everything is connected. John Muir said that everything is essentially connected. If you poke into one part, you discover that it's connected to the other parts. And that is very, very true. And when you're dealing with the atmosphere and the waters of the world and the temperature and everything that affects the earth, both the solid part, the atmosphere, the biosphere, the hydrosphere, you get a interconnected result that may be a little bit different than what you anticipate. Here we go. Just the other day, the carbon dioxide concentration at the Mauna Loa Observatory out there in the middle of the Pacific, where there are few sources of anthropogenic carbon dioxide. And this goes back to 1960 when they started measuring. Back in the mid 60s, early 70s was when James Hansen started looking at this. In the 80s, he went before Congress. That's where we were here. And then look where we are just the day before yesterday or a few days ago. We're very, very high, well above 410 parts per million. And the ups and downs in here are the uptake of carbon dioxide by plants and its release in the winter season. This is mostly uptake in the land-rich northern hemisphere, particularly the boreal forests and the tundras and steppes of the Russian Siberia. So this is a concern. We know it's happening, we can measure it, and we've got satellites now that can actually zero in on where it's coming from in specific. This increase means that this blanket here that we talked about a little bit before has gotten much bigger, much thicker, and that this loop is causing more and more circulations of that heat energy, and the blanket is getting bigger. It's like throwing more and more blankets on as time goes on. Here's the temperature. This is global mean temperature, mainly on land. And again, you see that in 1850, there's ups and downs all the time. That happens on Earth, but the trend is certainly up. And this is sort of where we are now. Some people think this is COVID here, and it might be. Here is temperature of the land and the ocean. And the ocean buffers things a little bit. The ocean's very big, can accumulate a lot of heat energy. Land would be certainly hotter if there wasn't an ocean to absorb the heat energy. The ocean also absorbs a lot of carbon dioxide. It fuses and dissolves right into the ocean. And so that carbon dioxide is not warming the earth, it's just going into the ocean. So things would be worse if we didn't have an ocean. So the bad things observed, you see this on the news every night, variability of seasonality and weather. You know, you have a tendency to think that, wow, spring might be coming a little early. You have to tap your maple syrup trees maybe in late February instead of late March, and other kinds of things like that. Your planting times on the back of your seed packets are different in terms of planting zones. We have had longer and hotter heat waves, more severe and damaging storms, more severe drought. The whole western side of the United States is in fairly severe drought right now. We've had more severe floods, and this is all kinds of flooding. The wildfires are always in the news from California and out west, again, contributed to by drought, but also by something called the Santa Ana winds, which are wilder, stronger, and more frequent, essentially because of changes in the climate. And we've had a lot of crop failures from variable weather. More bad things, wildfires and torrential rain-induced landslides. When those wildfires occur in California, they ceramicize or turn into a ceramic, smooth, hard surface, the clay layer under the surface soil. And the heat does that, just like you might fire a pot in a kiln. And then when the rains come later, it washes the loose soil and other debris from on top off, and that causes very severe landslides. And there's been great amounts of land lost that way, and a lot of property. Storm-related flooding and saltwater intrusion from sea level rise. This is a big problem in Florida, and the people of Florida are really concerned about that. The sea level rise is not very much now, but if those ice sheets in Greenland and Antarctica melt, it's going to rise further and faster. The sea also rises because it's getting more warmer, and when a warmed ocean expands in volume, essentially, and that causes the sea level to rise. Coral death from ocean acidification, melting of Arctic sea ice, changes the reflectivity of the Arctic. The sunlight goes into the sea, which absorbs it quite nicely, and it warms the sea. It doesn't reflect back out to space as it would if the sea ice were there. Melting of sea ice doesn't cause the sea level to rise, however, but the melting and calving of the freshwater glaciers that are on land in Greenland and Antarctica and in mountain glaciers, that does raise sea level. And then the melting of permafrost, methane releases actually enhance the warming and create more carbon that's not anthropogenic in the sense that it's created by burning fossil fuels or that sort of thing, but it's naturally held in a frozen state under the permafrost and in methane clathrates under the sea. And if things warm up, then that is released, and that could be a hidden danger if a lot gets released all at once. This is just a kind of a busy diagram of the 1980 to 2018 $1 billion weather and climate disasters. This is causing a lot of problems for a lot of people in a lot of places. And your insurance rates are going to go up because this has been going on, and insurance adjusting will have to pay out as this trend continues. And you can see that there are some spikes, certain really bad years, but again, the trend is upward. The US 2021 $1 billion weather and climate disasters are shown in this. And these you probably remember from the news: the tornadoes, the severe straight line winds from severe thunderstorms, hurricanes, wildfires, flooding, and the drought that has affected so many parts of the West. The tornado hitting Mayfield, Kentucky has been in the news. And of course, several tornadoes swept through 6 Midwestern and Southern states in December, killing at least 70 people. This is that candle factory from Mayfield. And, you know, a tornado like this has happened in the past, but it's not normal to get a tornado in December. But then it's not normal for it to be 73 degrees at night, said Mayfield resident Tim Weatherby, referring to the temperature on that day and that evening when those tornadoes came through those many states, essentially in the Ohio Valley, and destroyed huge amounts of property and caused billions of dollars of damage, and then killed a lot of people. We remember the hurricane series: Hurricane Harvey, Hurricane Irma, Hurricane Maria, all in the same year, a few years ago. And these were very, very severe hurricanes. And we had a very active hurricane season this year, but they did not make landfall. You can have severe hurricanes that stay out to sea and don't affect too many people, but then again, sometimes they come ashore and you get a Hurricane Katrina or hurricanes of that sort that do tremendous amounts of damage. The Santa Ana winds I mentioned before have set up in stronger and more frequent ways out in the West. And these winds really make things very, very dry. And when an ignition source happens, they create the wildfires. And these wildfires have not only been forest fires or brush fires, but they've wiped out entire towns, very much the same way that the tornado wiped out the cities in Kentucky. Landslides, I mentioned the clay layers and baking them, and all of California downstream from where these wildfires occurred are susceptible to this kind of landsliding and flooding when the rains finally do come from atmospheric rivers in the winter time, typically in California, and it washes all of that down, and it just inundates the cities that usually are at the foothills of these forested hills and mountains. Sea level rise, Miami Beach flooding has increased dramatically over the past decade. You can see some of the condo structures here. This is salt water, by the way, and this is not a storm. This is not a hurricane. This is just a high tide. And they get this happening more and more frequently on South Beach, in Miami Beach. And it causes terrible, terrible problems for the buildings along the side. And the water goes into the understructure of this and saturates the concrete and the metal with salt water. And that is not good. And the integrity of the building is compromised. And everybody knows about the Gulf Shores condo collapse. They're currently going back and forth looking at these buildings to see if they are subject to the same kind of problems. Now, Gulf Shores was fairly old as these things go, and maybe the more modern ones are going to be a little bit less conducive to this erosion and the problems caused by salt water. When salt water gets into a slab of concrete, it goes after the rebar and rusts it, and it goes into the concrete, the pores in the concrete. And when the water evaporates, when things get drier, the salt crystallizes and expands, and it actually causes that concrete to crumble. Here's another picture. This is a very, very built up area, and you can see how close the water is here and how close to the beach this is. This is going to be a major problem. If we get major sea level rise of 20 meters or something like that, of course, all of this is going to be gone. It's going to be washed away. Global food supply, another important area. My Ph.D. was in agricultural geography, and I looked at world food supply in a very detailed way, along with changes in climate that affected food supply. And the basic staples of corn, wheat, and rice are vulnerable to changing temperatures and to changing precipitation regimes. They don't do too well if temperatures get too hot or they get too cold, or if things get too wet or they get too dry. And even things like peaches, Georgia peaches, the crops was essentially lost by a warm winter because the chilling requirement was not reached that particular year. In other years, it's a freeze that wipes out certain crops, from peaches to blueberries to cherries in my own backyard. Wisconsin cherries up in Door County have been affected by changing climate. It gets warm in February and the cherry trees think it's time to blossom, and then you get one of those cold snaps in May, and it just devastates the whole crop. Florida orange production is at an all-time low. This is not just due to climate or freezes or that sort of thing, but the fact that it's actually gotten warmer and it's made for and wetter and made for a more conducive environment for a pest insect. And these insects carry a disease called greening disease or Hulin-Bong disease or HLB disease that has just wiped out the Florida citrus industry. And there are a lot of people that believe that it's the changing conditions with this organism that created this basic problem. The organism was introduced in California where things aren't quite as warm and quite as wet, and it hasn't done or had the same effect. This is an interesting one. This is corn. And of course, people in Des Moines and in Iowa know about their corn. And this is corn production. This is what corn likes. It likes temperatures that are sort of between 65 and maybe 88 or so. And nighttime temperatures included in this, and that offers the greatest production. And the changing climate has shifted this temperature curve over to the side, creating warmer temperatures. And there's some concern that it's actually going to create warmer temperatures over a very long period of time. They might not get as extreme, but they'll be warmer over a longer period of time. In both cases, having the temperatures on this side will make it difficult to produce the amount of corn that it usually is produced in the breadbasket of the US. Similar kinds of diagrams and optimum weather and climate conditions can be done for rice and can be done for wheat. And this is why we think that it's very, very concerning that the global food supply, particularly if temperature ramps up very, very fast, let's say through a big methane release or something like that, could lead to terrible amounts of crop destruction and lack of production, leading to big starvation in many parts of the world. Migrations have always been due to food problems, and that's not necessarily something that has not visited us these days. Political unrest, of course, is a big problem, and other kinds of things, hurricane damage, but food insecurity can cause very, very large numbers of people in a bad place try to seek a new place to get a good start and to have security in their food supply. And of course, this again is something that people fear. The US military really fears this because it can cause all kinds of geopolitical problems. It probably doesn't need stating that the Ukraine, the country of Ukraine, is sort of the breadbasket of Central Europe. And it is much more productive of grain than other parts of that part of the world. So geopolitical unrest and even wars can result from this kind of change in what can grow where and how accessible this is for the people. And of course, this is constantly in our news. It's constantly a political issue. And, how many people can you take? How many people should you take? We can't take them all. And of course, Europe is going through the same kind of thing with refugees from Libya and Somalia and Ethiopia. Ours are mainly from South and Central America, where there has been terrible problems with drought and also problems with the unrest, but maybe some of that is caused by the drought and the lack of food production, the failure of food production. Because climate change is caused by us, it can and must be fixed by us. And here we can see the various amounts of carbon dioxide, and most of it is fossil fuel. Some of this is projected. If the continued burning of fossil fuels keeps going and growing like it has been. And then some of it is due to deforestation, but there's been all kinds of attempts now to stop deforestation. Cement also contributes a little bit, and using cement, creating cement does release carbon dioxide. But this is the total, and you're going from 1950 to way up here, kind of this is where we are now. And it, of course, was showing that on that other diagram that we talked about before. This is cumulative CO2 emissions, and it shows that by country, the US has put out more over time. Much of what we've put out is sort of in the near term, but also the present. We've backed off a little bit. China has not had very much in the early days, but it has grown dramatically and is growing quickly, although there is an accord now in this discussion, I guess you'd say, to lower this part, which is the carbon from fossil fuels and cement. Land use change also can change this. And of course, China has a lot of people, so that can happen. And then the other countries are arrayed down here. A better way to look at this sometimes is per capita, per number of people in the country. And we are big emitters per capita. China, a little less so, but they've got a lot of people, and each individual person does not emit that much, but also you get a situation where they do, as a collective group, emit a great deal. And something's got to happen about China and some of these other big emitting countries to create the incentives and the will to change these trends and these patterns. Energy-related CO2 emissions by sector. This is essentially for the US climate source. And this is power, mainly the generation of electricity. And this is transportation. These have crossed a little bit recently as some of the power has decreased because they stopped burning coal in a lot of power plants. And that has been a big gain, I think, for lowered emissions. Industry kind of keeps going along. Industry likes things that save them money and save on their costs. And very often doing sustainability kinds of things will help that bottom line. Buildings, of course, not too much has changed there, and not too much probably needs to be changed. We need to look at these two sectors. One thing about this, the Green New Deal, I'm not a very big fan of that because it suggests that we put a lot of money and effort into weatherizing buildings and making them more climate adaptable. And if we could change this power structure to non-fossil fuel renewables, you wouldn't have to do this. You could have as much electricity as you wanted, and you could use electricity profligate in buildings. The transportation also needs to be mentioned because, of course, the changes in transportation might be that you make more fuel efficient cars and trucks, but also the trend is toward electrification or making hybrid vehicles, plug-in hybrids or just regular hybrids, and that has lowered the amount. But more people are driving, and if you put everything into electricity, then you've got to take it out of this power part here. And if you haven't changed this power to renewables, then you have to get that from somewhere, and that somewhere is probably going to be fossil fuels. Again, here, electricity and heat is the big one. Transportation is the second big one. Buildings are important, and we should do things to conserve energy in manufacturing and industry. Agriculture is not a big contributor, but there are places to save there. But these are the two that we need to really cut the per capita greenhouse emissions. This is where we are sort of now, and if we keep going without any climate policies, and this is kind of unrealistic because the climate policies are being put in place as we speak and have been for the last 15 or so years, but the current policies are more like down here, and we've got choices to make not to increase our emissions. This is the pledges from things like the Paris Accords. This would give us a 2-degree pathway, which would be fairly non-problematic, but 1.5, of course, is considered to be the ultimate. And the range here in terms of gigatons is very, very great. And our choices are going to determine where we are on all of these. And of course, these are models, but they also can be linked to models that go along with how much heating occurs. Again, this is an interesting one because it shows kind of the same thing. This is sort of the business as usual. It might come down, and then other kinds of strategies. But the negative emissions is an interesting one, and we'll talk a little bit about that further on. So it needs to be fixed by us at home. We need to educate the populace about the basics of weather and basics of climate and how the connected ocean works. People need to understand this. They will feel less befuddled by all of the complexity if they know even a little bit about this. And we need to do what we can at home to have a more sustainable lifestyle. And that means stop wasting energy. We would be in not as bad of a situation if we had our own energy practices such that we weren't wasting so much. And we should reward corporate responsibility. And there's been a lot of corporate responsibility, not necessarily in the energy sector, but among manufacturing and industry toward sustainability efforts. And we should reward that by purchasing products from responsible companies. This is a series of studies that have been done by Yale and other universities that show how the US population falls in terms of whether they're alarmed by the prospect of global warming, concerned, or whether they're cautiously concerned, I guess you might say. But the disengaged, they're not connected really too much and are not paying much attention. But there's large numbers of people that are still doubtful. Almost 20% are doubtful and dismissive. These people are real climate deniers, and they actually work against climate mitigating, warming mitigating factors. And this is over time, and you can see the alarmed has gotten bigger, a bigger share of the population, and so and more people from the concerned has moved up here. These have remained relatively the same. So we've got a climate in terms of what people think that is somewhat conducive to solving some of these problems. Everybody should be insulating their homes and their businesses. This is a win-win. It saves money, and we could cut emissions just because we wouldn't be using as much electricity or natural gas or oil to heat our homes. Fortunately, we don't heat our homes with coal anymore. It's actually a good thing that we have moved on from coal and steam to electricity. We can do just about anything with electricity that used to be done essentially with the direct burning of fossil fuels, or the burning of fossil fuels and converting that to steam. And we've made that transition already. It's not like we were in 1920 and had to do all of this. Saving water. A lot of people wonder why save water. We're near Lake Michigan, blah, blah, blah. Well, water saved is not water pumped, and pumping water is a big cost factor in terms of CO2 emissions. It takes electricity to pump water, and water saved is not water treated, and that also will save money. Compact fluorescents and LEDs are taking the world by storm, and this is saving us in terms of electricity used. And a lot of people are trying to get home solar, either rooftop or backyard solar. There are some places that make it very, very difficult to have rooftop solar or backyard windmills, and it should be encouraged, not discouraged, and certainly not made illegal. Low emission vehicles, the hybrids of Toyota captured the world's attention maybe about 10, 15 years ago because they save so much money. But now we've got plug-in low emission vehicles, and of course the no emission vehicles, the electric cars of the future are coming along. In Europe, probably about maybe 30% of the vehicles that are being ordered or being bought are electric. In the US, about 10%, which is really a very, very rapid increase, being held back essentially by the inability of industry to produce that many cars. People have to wait sometimes 2 years for one. They have to order them. And of course, some of the things that are put into the batteries are in low supply, but there are substitutions coming along the line, and that is helpful. And we have to take some national, rational, coordinated policies. Rational and national sometimes is an oxymoron, but we need to cut carbon and methane emissions. We need to put a price on carbon to encourage non-emitting opportunities or non-emitting alternatives. And we need to quickly shift away from the highest emitting, carbon emitting fuels. And of course, we need to remember, though, if we produce too many cars that are electrified and they're tapping into sources of electrification, such as been put into the infrastructure bill to put in thousands of these things all over the country, if the power coming to the plug-in is made with burning fossil fuels, particularly coal and natural gas and some oil, then it does no good. You may as well just fill up your tank with gas. You need to have the fossil fuels out of the picture in terms of generating the electricity. So we need to quickly develop these non-emitting sources. We need to create technology to carry and store the clean electricity from the best places to generate it to the places that have high demand for it in cities. Studies have been done by the engineering folks that have indicated we can, on relatively little public land out west, produce all the possible energy we could use, even with the fact that sometimes the sun don't shine and the wind doesn't blow. We really ramped up the energy production there, and we had a way to carry it so that it doesn't lose through voltage drop of the amount of energy that's in the wire. That would allow us to carry it to cities, and of course we need storage as well. So this is important. We need to create that infrastructure. One of the big problems that I have with the Green New Deal is it looks at low-hanging fruit of buildings and insulation and that sort of thing, and it doesn't address what would really solve the problem. Build out the wind farms, build out the solar, and do it in places that are not obnoxious to people, out in the Great Plains where miles and miles of empty farmland that could actually be used along with the solar farms, and then get a DC, high voltage DC pipeline for that energy to carry it to Chicago and New York and the places where people will use it. We need to keep the corporate responsibility going and sustainability efforts by the energy producers. Hopefully they can invest some money, and some of them are, in these kinds of things. And we need to capture and store underground carbon that can't be cut. And that's called carbon capture and storage. And we need to adapt to change already in the pipeline, because, and we need to be resilient so that we can take into account the extreme events that will come in the future. Germany has done a lot of this already, and this is a kind of a difficult graph to read, but they have cut greenhouse gases emissions by sector between 1990 and 2019, and this is the projected decrease in the future. Now, the gas pipeline from the Soviet Union might have some effect on this, but remember, natural gas produces half or maybe even less greenhouse gases than coal, which was a prime electricity source in Europe. So it can be done. China also is making big strides. They have a different approach. I went to China several times and visited some of their facilities, and a lot of their factories have changed to very, very efficient means of production so that they don't use as much electricity, and they're low emission in terms of the products they create. Even their beer in Tsingtao Brewery is made in a very sustainable way. Unfortunately, right next door, they have a coal-emitting power plant. So that's the dichotomy in China and many other places of the world, including the US. So large-scale mitigation. I might also say that there's probably some very, very good progress to be made in nuclear. Nuclear power plants can be made smaller, more efficient, and much, much safer than they have been in the past, so that their likelihood of causing environmental problems is very much reduced. And that may need to be explored in terms of a power supply that remains active and online, no matter what happens in terms of sunlight or snowstorms or the times when the wind is blowing too strong or too weak. The Two Creeks Solar Farm is right nearby, and this is really a massive structure, and it's creating a lot of energy. There are two others in Wisconsin, and there are more on the drawing board. And some of the investors in this are actually power companies. So we need to invest heavily in negative emission technologies. We need to take a look at ways to remove carbon from the atmosphere. If we suddenly have a big influx of carbon, perhaps due to the melting of methane hydrates or the melting of permafrost, we need to have some way to get out of that bind. Bioenergy with carbon capture and storage is another area. Direct carbon capture and storage is important. This has been explored in terms of power plants. And if you could actually do this in an efficient manner, perhaps you could still use some coal in certain situations when the sun don't shine and the wind don't blow. Negative emissions, there are technologies that will draw out the carbon and then put it into storage deep underground. And these kinds of technologies are actually being explored. You can also do things, speed up the natural process of storing carbon. We know over the past, the carbon has raised and it's lowered and raised and lowered. So there's got to be a mechanism by which carbon in the atmosphere is drawn out. And that's done by geologic processes. So if you grind up olivine, which is actually fairly common rock, you can accelerate this process. And it's not really developed at an industrial level, but there are some places that are very, very close to showing how this might work. Research in geoengineering methods to lower the temperature, deacidify the oceans, and maybe fertilize the ocean with iron. If you put iron in the ocean, it will grow carbon uptake from organisms, primarily calcareous organisms that are part of the plankton in the ocean. So none of this will be easy, but we do know how to do it and can do it if we have the political will, and we have made a start. So we're not starting from scratch. The interacting pieces are a complex puzzle and will require intelligent implementation to make the changes that we all need. And we don't have a great deal of time left, but I'm not saying you have to do this by 2050. I don't put a date on it, but we've got to get started and we've got to get moving. And we need to continue the progress that we've made. But one thing we can't do is panic and use a lot of money and energy doing things in an uncoordinated way without thoughtful implementation. And there's been a lot of people that have proposed things that really just don't make sense. What we really need to do is take a look at Germany and Japan and a few of these other places that have made great strides and have developed effective technologies which could be easily implemented in other places of the world and get them going. So thank you for your kind attention, and I'd be happy to take your questions. And there's my email if anybody would like to look me up. I also, if you send me an email, I can copy this off for you. These are some of the books you might be interested in. Some of the very best are Experimenting on the Small Planet by William Hay. This is really a big, thick book, and it'll take you a long time to do it. This is a real thin book by Carrie Emanuel. Those are the two best ones. If you're a teacher, the Teacher-Friendly Guide to Climate Change by some of my colleagues, particularly Don Duganhaus, is another good source. And then Drawdown, The Thinking Person's Guide to Climate Change is an EMS book. Michael Mann has a few books out there that are really good. Reinventing Fire and anything by Amory Lovins is really great with regard to energy and how we use energy and what we can do to solve our energy problems in ways that do not take away the atmosphere and the temperatures of Earth that we have essentially evolved under. And Confessions of a Radical Industrialist shows just how industry can be very responsive to these concerns and step up to the plate and fix things on their own. So